Welcome to a new video lecture on cybersecurity, the forgotten issue in railways. Every single day, millions of us step onto trains, literally trusting our lives to these incredibly complex, highly digitized transit networks. We see the sleek cars, the digital arrival boards, the automated doors, but there's this invisible danger lurking right beneath the surface of all that modern convenience. Because as these systems have gotten smarter and more connected, a massive vulnerability has been left wide open. So today, we're going to explore exactly why cybersecurity has historically been, left behind in railway design, and more importantly, how engineers are fighting to fix it. Okay, let's jump right in. Here's our roadmap for today. We'll start with safety versus security, map out the infrastructure modules, and then dive into the cyber threat landscape. After that, we'll tackle the certification trap, break down what's called the black channel solution, and finally look at securing the future. All right, Module 1, Safety versus Security, two distinct goals. To really understand railway vulnerabilities, we first need to pull apart two vastly different engineering concepts. So here's the absolute crucial distinction we need to make. Safety, that is entirely focused on preventing, detecting, and reacting to accidental harm. Security, on the flip side, is all about preventing, detecting, and reacting to malicious, intentional harm. Think of it like a big public office building, right? The smoke detectors up on the ceiling, those are your safety devices. They protect you from an accidental fire. But the turnstiles and keycard scanners at the front door, those are security devices specifically designed to keep out someone with bad intentions. Now, for over a century, the railway industry really only had to worry about the fires, the accidental mechanical failures. They literally spent 100 years perfecting the smoke detectors. But historically, they never really had to worry about invisible intruders. And that intense focus on accidents, that's exactly why safety has always been the absolute priority. In the engineering world, we measure this using safety integrity levels, or SIL. When you're building a system where a simple mechanical failure could mean a catastrophic disaster, you have to definitively prove it won't just accidentally fail. Railway control systems demand the absolute highest tier of reliability out there, SIL 4. Look at the probability of failure for SIL 4. It's astonishingly small. We're talking a maximum of one random hardware failure every 1 billion hours of operation. Naturally, hitting that mind-boggling level of safety requires incredibly rigid, uncompromising design rules. Moving on to Section 2, the Railway Infrastructure Modules, a distributed network. Let's take a look at how this massive network actually pieces together. Because a modern railway isn't just a train sitting on a track anymore. It's this massive, interacting digital ecosystem, broadly divided into 5 core modules. First up, you've got the onboard system right inside the train itself, handling the immediate physical movements. Then there are the station systems, controlling platform doors, turnstiles, and those passenger displays. The wayside control sits along the tracks, coordinating the signals and the actual train movements. Now, that wayside control constantly talks to the Operation Control Center, which is basically the brain of the entire network. And finally, you have the business support systems running the ticketing, scheduling, and all the telecommunications. And here's the kicker. Every single one of these modules is constantly chattering with the others. This highly distributed setup highlights a massive inherent danger for us. For decades, trains ran on dedicated closed-circuit technologies. They were completely isolated. But today, the industry is rapidly shifting toward IP-based shared medium networks. A modern train is essentially a giant moving internet router at this point. But because this entire broadly distributed infrastructure was fundamentally designed before modern digital threats even existed, it is incredibly difficult to protect. Which brings us to Section 3, the expanding cyber threat landscape, a new reality. We're no longer just sweating over a break accidentally failing, we have to worry about someone actively trying to break it. And the threats facing these newly connected modules? They're severe, and frankly, they happen every single day. Hackers can launch DDoS attacks to just overload network ports. Just imagine a busy control center suddenly going completely blind to all oncoming trains just because its network is flooded with junk traffic. Attackers can use botnets to take remote control of infected servers. They can deploy malware to sneak deep into the system architectures. Then there's spoofing, where an attacker intentionally falsifies data. Picture a hacker imitating a track signal, right? Telling a speeding train that the track ahead is clear when it absolutely isn't. And of course, there's cyber fraud. Everything from stealing digital ticket revenue to locking down the whole transit network with ransomware. When you overlay all those threats onto the infrastructure map, the scope is pretty staggering. An attack on a seemingly harmless node, say a public ticketing Wi-Fi network or a passenger info screen, could potentially cascade through the local area networks and find its way straight toward the vital controls. Now, in a railway, things like smooth acceleration, sure, those might be considered non-vital comfort features. But functions like speed limiters and automated braking, those are absolutely highly critical. If a cyber intruder manages to falsify speed data and that cascades up to the central control, the physical safety of the train and everyone on it is instantly compromised. So staring down this terrifying, highly connected landscape, the logical question is, why can't safety and security just coexist? Like, why don't the engineers simply slap some heavy-duty antivirus software and commercial firewalls directly onto the train's vital braking computers and call it a day? Well, that leads us right into Section 4, the certification trap, an engineering dilemma. This is the massive technical roadblock at the very heart of the issue. Remember that incredibly strict SIL4 safety requirement we talked about earlier? To achieve that, manufacturers are forced to follow incredibly rigid, mandatory laws, like EN 5129 over in Europe. If a device controls vital operations, it must be certified to be completely fail-safe. Security standards, on the other hand, like IEC 62443, are largely just general recommendations. They aren't strictly enforced for railways. So you have this wild dynamic where security is essentially optional, but safety is literally the law. And that legal rigidity creates a brutal paradox for the engineers. Let's walk through it together. Step 1, you build a vital braking device and spend months, maybe years, getting it perfectly safety certified. Step 2, a new cyber threat emerges, which, let's be real, happens literally every day. Step 3, you write a patch to update the security software to defend against this new hacker. But then, step 4, applying that patch changes the software of your safety-certified device. According to those strict safety rules, any modification whatsoever means the device is no longer certified, because regulators can't guarantee that those new lines of security code won't accidentally interfere with the physical braking mechanism. The certification is instantly voided. You'd have to fully recertify the train's brakes every single time you update its antivirus. It's practically impossible. So how do we fix this? Section 5, the black channel solution, engineering a way out. Let's look at the absolutely brilliant workaround engineers are using to bypass this trap. The solution relies on a very clever concept called the black channel principle. Basically, this is a method where the communication data itself has built-in mechanisms to detect if it's been messed with. It creates this protective safety envelope right over the data. Think of it kind of like sending a wax-sealed letter in the mail. If that wax seal is broken when it arrives, the receiver, in this case our vital safety device, instantly knows it was tampered with in transit, and it just ignores the message entirely. Because the safety devices can independently verify their own messages, it suddenly becomes possible for strict, certified safety devices and frequently updated non-certified security devices to safely hang out on the exact same network without ever interfering with each other. To see how this actually looks in the real world, consider a network intrusion detection system, or a NIDS. The highly regulated safety modules sit securely behind a dedicated safety layer. Meanwhile, the NIDS is both logically and physically separated from them. It hooks directly into the broader communication protocol rather than forcing its data to pass directly through the critical safety hardware. The brilliant payoff of this whole architecture is that the security modules act merely as network sniffers. They just quietly sit on the network, monitor all the traffic zipping back and forth, and actively watch for malicious patterns or intrusions. And because this intrusion detection system is completely decoupled from the safety-critical tasks, it doesn't require safety certification. An engineer can push software security updates to those network sniffers every single day to fight off the newest hackers, and the underlying highly regulated safety certification of the train's vital systems remains completely intact. It's a total game changer. Which brings us to our final stop, Section 6, Securing the Future, the Path Forward. Let's look at what needs to happen to make this the global standard. To really weave security directly into safety designs moving forward, the industry absolutely has to stop treating cyber protection as an afterthought. First, we've got to aggressively prioritize protecting vital functions, like speed and braking, over the non-vital ones like station displays. Second, those optional security recommendations, they need to become mandatory, unified regulations across all borders. Third, we need to standardize safety-compatible message encryption so these vital devices can verify their data in real time without any lagging. But crucially, none of these technical fixes will matter without real human cooperation. Governments, certification bodies, and railway manufacturers all have to collaborate tightly to build a common, unified cybersecurity framework. The tools to secure our interconnected transit networks do exist, and engineers are constantly finding innovative ways to deploy them without sacrificing that gold standard of mechanical safety. But as the gap between closed legacy systems and wide-open IP networks continues to shrink, it leaves us with one critical question to ponder during your next commute. Are our infrastructure upgrades moving fast enough to outpace the modern hacker? Thanks for joining.